reservation is now, and it's like someone I know, but I'm not like super close with, is sitting in there, and I'm like, hey, I reserved this room. Can you get out?
It's on with you today.
Yeah. I don't know. I guess the heat kept everybody.
Alright, we're continuing, right?
I mean, I missed.
Fine.
I missed a lot of the last class. So.
I think you did grow. So we have to find.
Okay. Apparently Sebastian is coming, but his car broke down, and he's waiting on AAA.
I hear excuses. His car broke down on the way home from the beach.
I don't know. Maybe.
Projectile motion rectangular, right? RT.
This movie I'm gonna have to do opening for it by myself. Yeah.
That's its vector form, right? If we make the assumption we set the initial launch point as the origin, so 0, 0. That would make x naught 0, y naught 0.
I'm guessing you always just assume that unless otherwise do.
Yeah, generally speaking, it's probably a good idea to set that as your origin. Okay.
So this might be an odd question, but is projectile motion, is it like a standard coordinate system, or is it spherical motion?
Projectile motion we generally take as rectangular.
It's rectangular. So the R of t is, I guess, what in this case, just a function of it.
RT is the vector, position. It's the position vector.
Gotcha. Okay.
Start with x equals v naught t cosine theta soft t. Now plug that into y. I forgot. Got some data there. All right, now just some algebraic manipulations. And what you should get after much algebra. And this is then, that shouldn't be y of t, sorry. Y of x. This would be your model for projectile motion written in the form of y of x. Or your height as a function of x. Second, they wanted the range. Range is the horizontal distance covered. We'll find out when you reach your initial position again. But if t equals 0, that's just the launch time. That's the starting time, so we don't care about it. So that's the one we want.
So where do you get t equals 0? Like, I get that it's the launch time, but why are you saying t is 0?
Step back and t out, right?
Yeah.
Product of two numbers is 0 means one of them has to be 0.
Gotcha.
So t is 0 or that second quantity is 0. We ignore the t equals 0.
Because you need understanding this stuff for something.
And this is gives you t is 2 v naught sine theta over g, right? Now plug that in to x. V naught t cosine theta. Which can be simplified, right? There's your range. V naught squared sine 2 theta all over g. So that means that your range is a function of two things. It's a function of your speed, your initial speed, right? Speed at which it's launched, and the angle at which it's launched. Those are the two factors that will affect how far the projectile goes. Find maximum range. We're going to make the assumption, and it's a very safe assumption, that the launch speed is arbitrary, but it's fixed. Why is this a safe assumption? Think of a cannon. For the most part, it's going to launch cannonballs at the same speed every time.
So I guess
You're not really changing muzzle velocity. You can't really change the muzzle velocity.
yeah, I was gonna say, so I guess by fixed, it's just saying like you go outside.
It can't be changed for that one. Now, a different cannon might have a different muzzle velocity, right? But then that muzzle velocity is still fixed.
So I guess it wouldn't be fixed if like something like
Well, no, it's still not changing the initial velocity.
oh, for initial velocity.
Yeah, and of course, for projectile motion, we're ignoring drag. And, you can deal with that in differential equations.
Yeah, I was gonna say, wasn't this like almost the equivalent to a question on the differential equations?
Except that was only one direction.
Yeah,
That was
I had no
one-dimensional, not
idea
two-dimensional.
I had no idea what to do with that question. To be perfectly honest.
Should be 10.
I had no idea what to do with that question. I was like, this isn't clicking, but no, this makes more sense.
How do we maximize something? Since we're assuming that V naught is a constant, we can only differentiate with respect to one variable, and that's theta. There's nowhere where that is not defined. Now I just said it equals 0.
What is, you know, so,
We're differentiating with respect to theta, not V naught.
oh.
Oh, I'm sorry. I'm just thinking that was 1, it's not, it's 0. Cosine of 2 theta has to be 0 in that case, right? Where is cosine equal to 0? Odd multiples of pi over 2. Two theta has to be one of these infinite number values. That means theta itself has to be an odd multiple of pi over 4. But theta's long triangle, right? What are the realistic values for theta? I'm just ignore these. I'm saying in general, theta's a long triangle. What's your realistic domain?
Like 25 degrees to 90.
I agree to the 90, except
I
radius.
guess 0 then. 0.
0 pi over 2. You could ignore pi over 2.
Well, yeah.
Be open at pi over 2.
0. So
0 straight ahead.
yeah.
I still projectile.
Okay. guess it's just most stage.
Well, wouldn't be, right? If you launch something 0 degrees off this table, gravity still affects it. So it's still going to arc downwards. Just because we set our origin to be 0, 0 doesn't necessarily mean it's 0, 0. Gravity is still affecting it. And 90, it technically could have pi over 2. It's just it's just going to go straight up and straight down, and they're basically free fall at that point. Well, we want the theta that's between 0 and pi over 2. There's only one of them. It's pi over 4. We now make use of the second derivative test. Derivative of that would be negative 4 v naught squared sine of 2 theta over g. Evaluate that at pi over 4. It's less than 0. Which means that that is an absolute max. So you maximize the range if your launch angle is pi over 4, and the maximum range v naught squared over g. Right, so once you have your launcher, if you want to maximize range, you just make sure it's set at an angle of pi over 4 above the horizontal. And that'll maximize, again, horizontal distance, that's the range.
I would assume that's not the
We're ignoring air resistance.
Oh no, I mean just in like this is like only the X ring this
For any projectile.
Oh, for any, okay, yeah, that's what I was just saying.
It's for any projectile, right? Because we didn't specify an actual column. We just did this for the arbitrary projectile. Projectile launched at a speed 500 feet per second at an angle 45 degrees to the horizontal. Determine speed and direction of the projectile after 5 seconds of flight. V naught is 500 feet per second. It's cosine of 45 degrees, root 2 over 2, right? Sine of 45 degrees is also root 2 over 2. That would be our model, right? Now we can find velocity. Which number is what? Derivative of position. Actually, 250 there. We have two choices now. We can find speed as a function of time and then plug in 5 seconds, or find velocity at 5 and then find the magnitude. Probably easier to plug in 5 first. What's 250 squared? 25 squared. Is what? 25 squared.
Squared.
625. 10 squared is 100, 625 times 100. Would be 62,500, right? 62,500. Double that, because I'm also going to have another one right there, right? Oh, I'm sorry. Double it and then double it again. Because we need to. Oh dear. So 62, what's 625 double? What? 625 double. 1250?
Yeah.
And then add 2 zeros to that.
100.
So 1.25 million, I think, right?
100.
Yeah. And then I have to double that, so 250,000.
So it's
Minus
square root for 250 squared
times 2.
minus 2. Minus
And then there's going to be another one there.
yeah, minus the same.
So that's why I'm doubling.
Minus 25 squared.
Right. Now, no, it's going to be plus 25g squared minus
Yeah.
twice the product.
Which is negative.
So 5 times 250, what's 5 times 25? 125?
Yeah.
And then add a 0. And then double it.
Should we just do the same number we just done?
With less zeros.
Why was 250 squared times 2?
I'm not doing 250 squared. I'm doing 250 times 5.
Yeah.
This term squared got absorbed. Right, because there's this squared plus this whole thing squared.
Oh, I see.
Right? So that's why once I found this, I double it.
Okay.
Now it's twice the product. Right? Because I'm expanding this square, twice the product.
Okay.
1250, so it's what, 2500? And then plus 25 g squared. We can actually factor out a 25, square root of 25 from all that, right?
So that's going to be the speed after 5 seconds.
So 25 divided by 250,000. Just 100,000, isn't it? Or 10,000. 10,000.
Yeah.
Minus 100 square root of 2 times g plus g squared, there's your speed. Feet per second. If we take the approximation for g of 32 feet per second, you should get about 403 for that. That's about 403 feet per second, but I'm going to leave it in that form.
Because you're going to want to assume G's.
Well, g would be, the approximation for g in empirical is 32 feet per second.
Oh, right, because G's just.
But that's an approximation. And that is also assuming that that value is constant, which it's not. It's actually determined by how high you are.
I'm not getting into this.
It is a slight change. It's a very small change,
Not taking the bait.
but it is technically not constant.
Not taking the bait.
You did once already.
Yeah, I know.
So if you want to weigh less, just increase your altitude. If you really want to weigh less, get into synchronous orbit and then jump out of the rocket jet. Now you weigh nothing. Because you're in free fall. Problem is that means nothing. You're probably going to die eventually. And they want a direction too, right? Direction is going to be given. The y component of velocity over your x component. Which can be simplified so direction would then be the inverse tangent of 50 root 2 minus g all over 50 root 2. And that is measured with respect to the horizontal.
So what was the WOT?
With respect to.
Okay.
And again, you plug in the approximation for g is 32 feet per second. You're going to get about 28.7 degrees with respect to horizontal. And so that's the direction of motion. And then this one's fun. Point is moving along the circle given by r cosine theta, r sine theta with a constant speed v. Show that if the radius vector to p moves with angular velocity of omega and angular acceleration of alpha, speed is radius times omega, and acceleration, magnitude of acceleration, is the radius times the square root of omega to the fourth plus alpha squared. So derivative of our position. And it's with respect to time. R dot cosine theta. R dot cosine theta minus R theta dot sine theta. That's the first component, and then there's your second component. But theta dot is omega. Yes. R dot is V. Sorry. R dot is 0 because it's the radius. The radius of the circle is constant. That would be R dot, which is velocity. Differentiate that, that'll give us acceleration, right? Does omega change with respect to time? It does. Once again, r dot's going to be 0. Radius doesn't change. Omega dot is angular acceleration. Right, and then theta dot, again, is omega.
What are the dots be?
Derivative with respect to time. That was V. Let me actually write this as a theta. So magnitude of that, absolute value of R, times the square root and the sum of the squares. But R is radius, so it's always non-negative. Under that square, you're going to have what? Omega squared sine squared plus omega squared cosine squared. Just leaves you with omega squared, right? Square root of omega squared, absolute value of omega. So I'm going to make an assumption here. Fix that spelling too. We assume that it's a positive angular velocity. So it's going counterclockwise. In which case you just get rid of the opposite values. And acceleration. Absolute value of R times the square root times that square root. Alpha squared sine squared, right? Plus alpha squared cosine squared. And obviously, again, R is non-negative, so absolute value is going to be R. 2 times alpha omega squared sine theta cosine theta minus the same thing. They drop out. omega to the fourth cosine squared plus omega to the fourth sine squared. Just omega to the fourth. Which is what was to be shown. That's motion in space. Any questions on motion in space? Go away. So work on that worksheet until 2:15. 10-minute break follows. 2:25 we begin multivariate functions. Multivariate functions. And just as they sound, functions that have more than one independent variable. And all the functions we've looked at thus far have been single variate. Right? They've had one independent variable, typically in the form y equals f of x, right? Now we're going to look at functions that have two or more independent variables. For the most part, our studies will be restricted to 2 and 3 variate, but everything can be generalized to more than that. So this is a function of two variables. Z equals f of xy maps an ordered pair xy in a subset of the plane R2 to some real number z. Right, you saw, of course, your domain set. The set D is your domain, and then the range is all the values of z. So notice what this is doing, right? It's essentially adding a height to each ordered pair. And then you have your level curves. So level curves are just all the curves f of xy equals c. C is some real number in the range. And the plot of all your level curves is called a contour map. You also have vertical traces. For a two-variate, you have two types of vertical traces. You have the vertical trace for x equals a, which is f of a y equals z. And then you also have your traces for y equals b, which will be f of x b equals z. Right, both a and b are just going to be constants. And then three-variate functions of the form w equals f of x, y, z. This maps ordered triples in space to a unique real number W. Right? So that's set of ordered triples is the domain. All your values of W is the range. And again, notice what this is doing. This is taking a point in space and giving it a height. Height in the fourth spatial dimension. And there's no way to visualize the fourth spatial. Level surfaces, same as level curve, except it's now f of x, y, z equals c. I'm going to let you read through a lot of this on your own. This is setting up the theory needed for multivariate limits. Formal definition of a two-variate limit. Again, read through that. You have your limit walls. Limit of constant still a constant. You take the limit as xy versus ab of x, it's just a. And the limit of y would just be b. So they would then behave like single variate limits. You have your sum difference law, which still holds. Right? So the limit of a sum or difference is just the sum or difference of the limits. Limit of a constant multiple is just the constant multiple of the limit. Limit of product of the limits. Limit of the quotient of the limits, as long as the limit of the denominator is not 0. Limit of power of the limit. Limit of a radical is the radical of the limit, as long as the limit is non-negative for even indexed radicals. Continuity defined the same way as it was for single variate, except it's now two variate. And all of this can be extended to more than two variate. For single variate, if you wanted to show a limit did not exist, just show that from the left and from the right are two different values, right? Right, so the function behaves differently left and right. So you show the limit doesn't exist. All right, so here's AB. How many ways can you approach that point? How many directions can you approach that point from? Huh? No? Well, ignore all this up here. Just give them a point. I want a plane. How many ways can you approach that point? Yeah, there's a limited number of ways. Unlike the two ways you can approach a point on an axis. To show that a limit does not exist for multivariate, you have to show that there are two distinct paths that when you approach the point, you get a different limit. But at the same time, simply showing that the limit's the same for a finite number of paths is insufficient now to show that the limit exists. Because you have an infinite number of them. So in general, multivariate limits are a bit more of a pain in the ass to work with. Right there. That's right. Start off simple. Evaluate a multivariate function. It's going to behave the same way as with single variables, right? Order matters. This is f of x, y. So you have to keep the same order. So what we'll do, everywhere there's an x, plug in -1. Everywhere there's a y, plug in 3. It's just 2, right? And again, this can be extended to any number of variables. So what's -4 to the 4th power? It's -4 to the 4th. Could we make this even easier? -1 to the 4th as well. +1, right? 4 to the 4th? Isn't 4 2 squared? So 4 to the 4th is what? 2 to the 8th? Times 2 is 2 to the 9th. What's 2 to the 9th? We don't have our powers of 2 memorized. 2 to the 9th. No. Because you haven't worked in base 2 a lot. It's 512. You're left with what, 508, right? Guess we don't have any comps like you over here. Comps I should have done 2 to 9, but I thought I had. They work base 2 all the time. I think comp size now up to what, base 128. I think the 128-bit operating systems aren't publicly available, but I'm pretty sure there's a 128-bit operating system, which means you have to work base 128. Right now, the operating systems are base 64. They're 64-bit. And a lot of coding, I think, is also done in hexadecimal, which is base 16. Right, so evaluating multivariate functions, not that difficult. Same as with single variate. I'm going to plot contour maps. So you could try and do this by hand. No, stop here. It's more fun. Use the contour plot. So it's just the function. You now need to give range of values for x and a range of values for y. So essentially set up your viewing window. Let's do start with -5 to 5. See how that works out. And that is technically all you need to get a contour map. There's our contour map. Not really like that. We can add plot legend, which will show you what those shades mean. Right, those shades for a contour map just give you the different contour levels that are used. Right, so based on this, what we can read is this color represents c equals 0. So this line would be for c equals 0. Then this would be -10, because the shading represents c equals -10. Then -20, -30, -40, -50. Right, those are your contour levels. And I don't like the fact that it's framed, so I typically turn the frame off, the accent's on. Let's get rid of the legend. Instead, I think it's shading. Turn off the shading. Now, if you hover your mouse over, the line is going to tell you what the contour level is. You can label that on the plot. There's contour labels. True. Now you can see that they are above. There's actually one below too. There's the 0, there's -50. -50, right? -40, -30, -20, -10. Now, by default, Wolfram chooses the contours for you. But, so this is its default, contours automatic. But you can also tell it how many contours to give you, so that would give you 10 lines, 10 contour lines, and it's going to automatically choose them. And it's going to be equally spaced. That's kind of the same thing. Use at most 5 automatically selected contours. If you set it up this way, you can actually tell Wolfram which values of C you want. You can list out what values you want. And you can also change their style. And we can get into some more complex things. I'm going to do just choose 5 contours. It's going to get rid of those. Notice they're only giving me negatives. Let's try and do this. -10, -5, 0, 5, 10. Let's see what that would give us. So there are no positive contours, which is a shame. So how do we want to do it? Doesn't matter, however you want. I'll stick with that, I think. What about for x squared plus 3y squared? So let's choose them for us. They started out at 10. So let's choose some. And of course, all of them have to be positive, right? X squared plus 3y squared is always going to be a positive value. Oh, which ones do we want to do? Now I'm going to do 0. 0 just being the origin. That's just going to and I'm going to do multiples of 3. That's a 21. And notice it's not actually showing 0 here, right? It's just that point there. So what if I asked you to specifically show that point? How would you do it? I'm actually going to use that. Oh no, it doesn't like that. It doesn't belong there. That's better. And now you can see that point right on there, right? And we could make that larger too, but that should be good. So next up was x squared minus 4y squared. Let's see what that gives us. Okay, not too bad. Let's try this. Kind of looks better. Right, it doesn't have to be symmetrical on each side, right? I could have kept going. I could have gone 25, 30, 35, 40, whatever. I tend to try to keep everything symmetrical. take a few minutes and think about what that contour map is going to look like. So what do you think the contours will be? And then I'll go ahead and plot it and see if you're correct. So what do we think?
Like incorrect, it's going to be your contours going down.
Do you think that the contours are going to be parabolic?
Yeah.
Do you have any thoughts? What it's going to be like? No. I'm going to judge it then based on that. If he's wrong, the entire class gets executed.
Yay, moving to school.
No, you'll be in school purgatory.
Nobody's proven them yet.
There's an easy way to find it.
Yeah, nobody's done it. That looks confusing.
They're just vertical lines.
Why?
C equals negative 4x squared solve for x. X squared is negative c squared. So x would be plus n minus the square root of c all the way to c is a constant. So x equals a constant, which is a vertical line.
So then why not?
That's y equals a constant.
Oh yeah. So yeah, I guess you're just.
So each value of c gives you two lines.
So then, for contours, you're just always solving.
It's f of x, y equals c. That's what a level curve is.
So
I sometimes call it a contour curve, where it's just a contour. And then the contour map is a plot of all the level curves.
So then you're just always solving for whatever variable, let's see. If it was like f of y, you'd be solving for what y.
Right, but you can't always do that. Like in this case, this would be c equals x squared minus 4y squared, which are hyperbolas.
So would you solve for x and then solve for y?
So- No, it's just those are the relations. Right, in this case, we could solve for x because we only have x. I think
So I guess it's good.
here you can solve for y because there's y minus 2x squared.
Yeah. Okay.
Right, but in situations like these where it's x squared minus 4y squared, Yeah. these you can't, right? These are not going to be functions. But if you x squared plus 3y squared equals some constant, that's an ellipse. Right, x squared over a squared plus y squared over b squared equals 1
So I guess
is an ellipse.
really just knowing
Yeah.
what different formulas graphs you make.
So what the relations look like.
So then how?
Whereas this is whereas these are hyperbolas.
So what determines the amount of functions?
Oh, you choose. Technically, I have an infinite number of them,
Oh,
right? Because for every value of sig.
Okay,
So-
it doesn't set-
Like on an exam, I tell you which values to sketch.
How would you
Right. So for instance, here
solve for these?
maybe I'd say sketch contour map using c equals 0 to 4 and 6. For instance, I could do.
So is it really just know what shape the graphs make? There isn't another way. There isn't like a good way.
Other than technology, no.
That's so. I don't like that. That's annoying. It's literally just memorize graph shapes and hope you get the right one. Hope you know enough.
No, that's what we had used to have to do when I was in school.
That's so dumb.
Because they didn't really have the technology.
Also,
they had.
what were contour maps used for? Like,
Are you familiar with maps that give you altitude?
yes.
That's contour map.
Oh, I see. Okay.
Right,
So
each-
then that'll be-
Because you'll have lines.
Yeah.
Each line represents an altitude. Well, that's contour.
Gotcha. Okay.
Or think of the temperature gradient maps
Yeah.
or pressure maps. Those are all contours.
Okay.
Those are all contour maps.
Okay.
Right? So they do occur a lot. You just never really think of it in that sense.
But I guess, was your P7? It's like unless you're the math maker, just reading them.
No, not unless you're the one doing it. But now you know, knowing what they are helps you to read it better. Helps you understand it. You can also think of the contour map as kind of like the shadow of the surface on the XY plane.
Okay.
It's a very rudimentary comparison, but you can kind of think of it that way.
Yes. It's just a very theoretical thing to wrap my head around. I don't know what to figure.
And then, of course, you have level surfaces, which we're not going to deal with. I don't make you sketch three-dimensional things. But they would be found the same way. It's for the three variable functions. And you use contour plot 3D in that case. But again, I'm not too worried about that.
So I guess drawing these is, that's so frustrating, that drawing these is just know the graph. So there's
Unless you're really good with your calculator.
Yeah, well, okay,
The
I
T-On's
gotta
fine.
talk to you about that, because they wouldn't let me use my 89 when I was testing some.
They should have. Down in
I know, I mentioned that, and they read that, and they still told me no. I'll talk to you about it after.
For which class? Both?
But, yeah,
I'm not talking, because I was told I could.
I was told
If I put down any model, they told me that.
I was just told by both of the staff that they never let anybody use an 89 or higher.
That's not true, so I've done it the best.
They like also like memory like the calculators before you go into the so I think that that's something to do with it.
Assuming, well, this is nice can write g of x plus h of y, right? What's the domain for root x?
I guess x is greater than 0.
So the domain has to be where the function is totally defined, right? Well, it means both x and y have to be non-negative.
Could you also write it as the absolute value of one is the domain?
And so that's write the set of all ordered pairs x and y such that x and y are greater than or equal to 0. This was pretty straightforward. Equation of a sphere centered at 10, 10, 4 with radius 9. That's all it is. And it's the same as circle, just one extra dimension. Domain and range here. But what's the rule for square root? What has to be positive?
What you're taking is square root.
Just positive?
No. Here it can be 0.
Not negative.
Yeah.
Domain is a set of all points, x, y, such that x squared plus y squared less than or equal to 4. What kind of region is that? What's the region?
The first region.
Hmm?
The first region is
So start with equals 4. What's x squared plus y squared equals 4? What kind of curve is x squared plus y squared equals 4? This is basic shape.
very.
X squared plus y squared equals 4 is a circle radius 2. So that'd be all the points on the circle. Less than 4 means it's all the points inside that circle. So the region is a closed disk radius 2. And everything on and inside the circle of radius 2. This is going to be important later. Now for the range. this way. If x squared plus y squared is less than or equal to 4, it's actually also implied that that's greater than or equal to 0. Right, so the domain is x is 0 less than or equal to x squared plus y squared less than or equal to 4. So this value here goes from 0 to 4. Well, at 0, this is just square root of 4, right? Which is 2. And then 8 minus 2 is 6. What happens as this value gets larger? This value gets smaller, doesn't it? Specifically, as x squared plus y squared approaches 4, doesn't this value approach 0? Which would mean that z itself approaches 8. So it has a lower bound of 6 and an upper bound of 8. That's your range. If x squared plus y squared is 0.
Mm-hmm. Oh.
So you're only ever going to get values 6 to 8 from that function. Again, domain and range, same definition as with single variable. Just now it's multivariate. When we come back, we'll look at limits. Have a good weekend.